There is a tunnel in the mathematics of space and time, one that no one went looking for. Welcome to the Sleepy Lab. Tonight, you will drift through one of the quietest mysteries in all of physics, a structure that lives inside the equations, uninvited, persistent, and strange. If you find this kind of wondering useful for sleep, consider subscribing, one sleepy soul at a time. Now, let's begin. In 1935, Albert Einstein was not trying to discover a tunnel through the universe. He was trying to do something far more modest. He and his colleague Nathan Rosen were working on a question about the smallest things in nature: electrons, particles, the fundamental pieces of matter. They wanted to know whether those particles might not be particles at all, whether they might instead be something purely geometric, little knots or bridges in the fabric of space itself. No substance, no stuff, just shape. It was a beautiful idea, and it did not quite work. But in the process of exploring it, something else appeared in the mathematics, something they had not asked for. The equations of general relativity, Einstein's own equations, the ones that describe how mass and energy curve the fabric of spacetime, produced a solution: a bridge. A connection between two separate regions of space-time, joined at a single narrow throat. It emerged the way certain things do in mathematics, not because anyone summoned it, but because the structure of the theory allowed it. And what the theory allows, it tends to produce. Einstein and Rosen published their finding that same year. They called it a bridge. We now call it the Einstein-Rosen bridge. And it is the earliest ancestor of what we today call a wormhole. To understand what that bridge actually is, it helps to sit quietly with what general relativity says about gravity. Because general relativity does not describe gravity the way we usually think about it. There is no invisible hand pulling objects toward one another. No force reaching across empty space. Instead, Einstein proposed something stranger and, in its own way, more serene. Mass and energy do not pull. They curve. They bend the four-dimensional fabric of space-time itself, the three dimensions of space woven together with the dimension of time, into a single continuous structure. And objects moving through that curved fabric follow the natural paths that the curvature lays out for them. What we feel as gravity is simply the shape of the space we are moving through. A planet orbits a star, not because it is being pulled, but because the star has bent the space-time around it into a gentle curve, and the planet is following that curve as faithfully as a marble rolling along the inside of a bowl. This is the foundation. And it is on this foundation that the wormhole quietly appears. In geometric terms, a wormhole is a handle. Imagine the fabric of space-time as a vast, thin sheet. 2 points on that sheet might be separated by an enormous distance if you travel along the surface. But if the sheet could fold, if two distant regions could curve toward each other and connect, then a tunnel through the fold would link those 2 points directly. Not by crossing the distance between them, but by bypassing it entirely. Mathematicians call this a handle on a manifold, a topological feature that changes the connectivity of a surface without changing its local geometry. Locally, everything looks normal. The curvature, the physics, the passage of time, all behave as expected near the tunnel's mouth. It is only the global structure that has changed. The shape of the hole. A wormhole is, in this sense, less like a hole and more like a seam, a place where two distant parts of the universe have been quietly stitched together. The simplest version of this structure is called the Schwarzschild wormhole. named for Karl Schwarzschild, who found the first exact solution to Einstein's equations, a solution describing the geometry of space-time around a perfectly spherical, non-rotating mass. When you extend that solution as far as the mathematics allows, when you unfold it completely, something unexpected appears inside. A second exterior region. A mirror universe, in a sense, connected to ours through a narrow geometric throat. The Schwarzschild wormhole. It is a real solution. The mathematics is exact, the geometry is well defined, and the bridge between the two regions is genuinely there. And yet, it cannot be used. Not by anything. Not by light. Not by a signal. Not by a single particle moving at any speed. The reason is time. The Schwarzschild wormhole does not sit still and wait. It forms, and it collapses. And it does both so quickly that even light, traveling at the fastest speed the universe permits, cannot cross from one side to the other before the throat pinches shut. The bridge exists, but it exists the way a soap bubble exists, for an instant, complete and geometrically perfect, and then gone. Any traveler who tried to pass through would find the tunnel closing around them before they reached the other side. Not because of any obstacle, but because the geometry itself does not hold. This is the first and most fundamental problem with wormholes as passages. They are unstable by nature. The simplest ones collapse before anything can traverse them. And the ones that might stay open long enough to be useful, the traversable wormholes that physicists would later explore, require something the universe does not obviously provide. But that is a question for another night. For now, let the image settle gently. Somewhere inside the mathematics of gravity, inside the same equations that describe the orbit of the moon and the bending of starlight around the sun, there is a tunnel. It appeared without being asked for. It was found by two physicists who were looking for something else entirely. And it has never quite gone away. The equations keep producing it. Quietly, persistently, as if the geometry of space-time has always known something about connection that we are only beginning to understand. You are lying still now. The room around you is quiet. And somewhere in the fabric of space and time that holds you gently in place, the mathematics continues. Patient and unhurried. Full of structures no one has seen. Full of bridges no one has crossed. Let that thought carry you softly. There is nothing to solve tonight. Nothing to reach. Only the quiet fact that the universe is stranger and more intricate than it appears, and that somewhere in its geometry, there may be a door. In 1988, a physicist named Kip Thorne sat down with a different kind of question. Not whether wormholes could exist inside the mathematics, that much had been known for decades, but whether a person, or a signal, or anything at all, could actually pass through one. He and his colleagues began working through what the physics would require, and what they found was both precise and quietly humbling. A traversable wormhole, one with a throat that stays open long enough for something to cross, cannot be held open by ordinary matter. Not by rock, not by gas, not by any substance that has ever been measured in a laboratory. The geometry of the tunnel demands something stranger. It demands matter with negative energy density. That phrase deserves a moment of stillness. Negative energy density does not mean cold. It does not mean dark. It means something more fundamental. It means a region of space whose energy is lower than the energy of a perfect vacuum. And that requires some care to understand. A vacuum, in the everyday sense, is emptiness. A room with all the air removed, a container with nothing inside. But in physics, a perfect vacuum is not truly empty. It has a baseline energy, a kind of irreducible hum that belongs to space itself. Quantum fields fill it, flickering in and out of existence, never fully at rest. This baseline is called the vacuum energy. And negative energy density means falling below it, having less energy than nothing. In a sense, less than the quietest, most empty region of space can ordinarily hold. No known material does this at any scale that would matter for a wormhole. No planet, no star, no engineered substance. The requirement sits there in the equations, patient and immovable. And yet, the universe does offer a small, quiet hint that negative energy is not entirely forbidden. It is called the Casimir effect. In the 1940s, a Dutch physicist named Hendrik Casimir predicted something that seemed, at first, almost too subtle to be real. If you take two flat conducting plates and place them very close together, separated by a distance smaller than the width of a human hair, something happens in the space between them. The vacuum between the plates becomes slightly different from the vacuum outside. Outside the plates, quantum fluctuations fill space in the usual way. Every wavelength, every frequency, the full restless spectrum of the quantum field. But between the plates, only certain fluctuations fit. The geometry of the gap constrains which patterns of energy can exist there. Longer wavelengths are excluded. The vacuum inside is quieter than the vacuum outside. And because the vacuum inside contains fewer fluctuations, it has slightly less energy. Less than the vacuum. Negative energy density in a thin and delicate sliver of space. The effect is real. It has been measured. The two plates are drawn gently toward each other by this imbalance, as if the quieter vacuum between them is pulling them in. The force is small, almost impossibly small, but it is there, and it is consistent with the prediction. This is one of the places where the quantum world and the geometry of space touch each other in a way that can be felt. And for a moment, it seems like a door. If negative energy can exist between two plates, perhaps it can be arranged, shaped, concentrated. Perhaps the requirement for a traversable wormhole is not as impossible as it first appeared. But the door does not open easily. The Casimir effect produces negative energy in quantities that are almost incomprehensibly small. The gap between the plates must be extraordinarily narrow for the effect to be meaningful at all, and the total amount of negative energy involved is a whisper, a fraction of what would be needed to hold open even the smallest conceivable wormhole throat. To scale that effect up to wormhole-sustaining quantities would require arrangements of matter that have no known physical realization, structures that would need to be engineered at scales and densities that appear, by every measure physicists currently possess, to be beyond what the laws of nature permit. The numbers do not close. This is not a failure of imagination. It is a precise result. Thorne and his colleagues worked through the requirements carefully, and what emerged was not a blueprint, but a boundary. A clear statement of what would be needed, and how far that need exceeds anything the universe seems willing to provide. There is something almost meditative about that kind of result. A question asked with full rigor, an answer returned with full honesty. The universe does not say the thing is impossible. It says only that the cost is extraordinary, and that nothing in the known inventory of matter can pay it. The wormhole remains open in the mathematics, and closed, for now, in the world. Somewhere between those two facts, physicists have spent decades sitting quietly, turning the problem over, looking for a material, a mechanism a quantum effect that might narrow the gap between what the equations allow and what the universe provides. Some have looked more carefully at quantum fields near curved spacetime, where the vacuum energy behaves differently than it does in flat space. There are configurations, theoretical, carefully constructed, where quantum effects produce regions of negative energy density without requiring exotic classical matter. These are not solutions. Exactly. They are suggestions. Hints that the problem may have more structure than it first appears. Others have noted that the averaged null energy condition, the precise constraint that exotic matter must violate, may not be absolute. Quantum mechanics, in certain regimes, allows brief and localized violations of energy conditions that classical physics holds inviolable. Whether those violations could ever be sustained long enough and arranged precisely enough to stabilize a macroscopic throat, that remains genuinely open. Not open in the sense of likely, open in the sense of unresolved. And there is a kind of peace in that distinction. The universe is not obligated to make its structures accessible. It is only obligated to make them consistent. A wormhole that exists in the equations but cannot be built is not a broken promise. It is simply a feature of a geometry that does not bend to convenience. The Casimir effect sits at the edge of this picture like a small, quiet light. It does not solve the problem. It does not bring the wormhole closer to reality in any practical sense, but it demonstrates something worth holding gently as you rest. That the vacuum is not nothing. That space itself has structure, and that structure has energy, and that energy can, in the right conditions, fall below the floor that ordinary physics sets for it. The universe contains, in the narrow gap between two metal plates, a region where space is quieter than silence, where the energy of emptiness dips below the energy of emptiness, where the mathematics of the very small touches, just barely, the mathematics of the very large. And in that touch, in that thin, measured, reproducible sliver of negative energy, there is a reminder that the universe still has rooms we have not fully mapped. Structures that do not announce themselves. Properties that emerge only when you ask the right question, in the right geometry, at the right scale. You do not need to hold any of this clearly tonight. Let it soften at the edges. The plates, the quiet vacuum between them, the tunnel that the equations keep drawing, patient and unbuilt. All of it resting now, the way everything rests in the dark. Unhurried, unresolved, and somehow still full of the quiet suggestion that space is more than it appears. And so the equations keep returning to the same uncomfortable place. Not just that negative energy is rare, or difficult to produce, or limited to the narrow gap between two carefully placed plates, but that even if you had it, even if you could gather it, shape it, hold it at the throat of a tunnel through space, it would have to behave in a way that ordinary physics does not permit. There is a rule, quiet but firm, woven into the structure of general relativity. It is called the averaged null energy condition. And it says, in essence, that energy, averaged along any path a beam of light might travel, cannot be negative. Not locally, not globally, not on average. The condition is not a law handed down from outside the theory. It emerges from within it, the way a river's banks emerge from the shape of the land. It is what space-time seems to require in order to remain well-behaved. Exotic matter, as physicists define it, is matter that violates this condition. Not merely unusual matter, not merely dense or cold or strange in its composition, but matter whose energy, measured along the path of a light ray, falls below zero in a way that the average null energy condition forbids. No known substance does this at any scale that would matter for a wormhole. The Casimir effect touches the edge of it, barely, microscopically, in a geometry so constrained it cannot be scaled. And so the wormhole remains, for now, a structure that the equations permit in principle and the universe declines to provide the materials for. There is another reason the universe may be reluctant. Stephen Hawking spent years thinking carefully about what wormholes would mean if they could be built and held open. And he arrived at a conjecture, not a proof, but a carefully reasoned suspicion that the universe protects itself. He called it the chronology protection conjecture. The idea is this: a traversable wormhole, once created, would not simply be a tunnel through space. It would, under the right conditions, become something far stranger. It would become a tunnel through time. The reasoning is quiet, but relentless. Imagine a wormhole with two mouths. One mouth remains at rest. The other is accelerated, carried away at a speed close to the speed of light, then brought back. This is not a thought experiment about science fiction. It is a direct consequence of special relativity, which has been tested to extraordinary precision. When an object moves at high speed, time passes more slowly for it than for something at rest. This is not an illusion. It is not a trick of perception. Clocks aboard fast-moving spacecraft run measurably slower than clocks on the ground. The effect has been confirmed with atomic clocks, with particle accelerators, with satellites. A clock carried at relativistic speed and returned will show less elapsed time than a clock that stayed behind. The two clocks, once synchronized, are now different. They disagree about how much time has passed. And a wormhole mouth is, in this sense, a kind of clock. If one mouth is accelerated and returned, it ages less than the mouth that stayed still. The two ends of the tunnel now open onto different moments. Step into one mouth, and you emerge from the other, not just at a different place, but at a different time. This is what physicists call a closed time-like curve, a path through spacetime that loops back on itself. Not a metaphor, a solution to Einstein's equations, a curve that, if you followed it long enough, would return you to your own past. The equations do not forbid this. They produce it, quietly, as a consequence of combining wormhole geometry with the time dilation that special relativity demands. And this is where the universe, if Hawking was right, begins to resist. The chronology protection conjecture does not say that closed time-like curves are logically impossible. It says that the universe arranges itself so that they never quite form. Hawking's argument was that as a wormhole approached the configuration needed to create a closed time-like curve, quantum effects would build up at the throat. Vacuum fluctuations, cycling endlessly through the loop, would amplify. The energy density would grow without bound, and the wormhole would be destroyed before the loop could close. The universe, in this picture, does not forbid time travel by decree. It prevents it through physics, through the behavior of quantum fields in curved spacetime, through a kind of self-correcting instability that erases the tunnel before the paradox can arrive. It is a gentle form of prohibition, not a wall, but a dissolution. And yet the conjecture remains unproven. It is a suspicion, not a theorem. A pattern Hawking noticed, not a law he derived. Some physicists accept it as almost certainly true, others are less sure. The mathematics of quantum fields in curved spacetime is difficult, and the calculations near a closed time-like curve are among the most difficult of all. What can be said, carefully, is this: Every known path toward a traversable wormhole runs into at least one barrier that the universe seems to place in the way: the exotic matter requirement, the averaged null energy condition, the chronology protection, instability. Whether these barriers are absolute or merely very high is a question that cannot yet be answered. There is something worth sitting with quietly before sleep. A closed time-like curve is a loop in time. An object following one would return to its own past, would exist, for a moment, in the same region of space-time as its earlier self. The grandfather paradox lives here. The question of what happens if a traveler reaches back and prevents their own journey. Some physicists find this sufficient reason to believe closed time-like curves cannot exist. The universe, they argue, would not permit a logical contradiction to become a physical one. Others are less certain about what counts as a contradiction. They point to the Novikov self-consistency principle, which holds that only self-consistent histories are permitted, that the universe does not forbid the loop. It simply ensures that everything within the loop is already consistent with itself, that the traveler who reaches back can only do what was always going to be done. There is no resolution tonight. There may not be one for a long time. What remains is the shape of the problem. A wormhole, if it could be held open, would connect not just two places, but potentially two times. The same geometry that curves space also curves time, because space and time are not separate things. They are aspects of a single fabric, and that fabric bends together. A tunnel through space is, under the right conditions, a tunnel through time. In the universe, as far as we can tell, as carefully as we can measure, seems to resist this. Not loudly, not with any visible mechanism. But every time the equations approach the threshold, something intervenes. The matter required is not available. The energy condition is violated. The quantum fields grow unstable. As if space-time has a preference. As if the universe, without announcing it, has already decided something about the shape of its own history. You do not need to resolve this tonight. Let the closed curves rest where they are, looping quietly in the mathematics, patient and untraversed. Let the wormhole mouths drift apart in the dark, one aging faster than the other, the gap between them widening into something that might, in another universe, be a door. The equations are still there, still producing these structures, unhurried, indifferent to whether we can build them. And the universe is still here, still declining, gently, to explain itself fully. Still full of rooms the light has not yet reached. There is a question the equations quietly raise, once you follow the closed curves far enough. If a tunnel through time could be traversed, if a traveler could step through one mouth and emerge before they enter the other, then the question becomes uncomfortable in a very particular way. What if the traveler went back far enough to prevent their own journey from ever beginning? This is the grandfather paradox, not in its most dramatic form, but in its simplest one. A loop that, if completed, would erase the conditions that made the loop possible. A cause that, if followed to its conclusion, would remove itself. It is not a paradox that requires malice or intention. It arises from the geometry alone. From the simple fact that a closed time-like curve, by definition, allows an event to precede itself. Physicists have sat with this for a long time. Some argue that quantum mechanics would intervene before any paradox could take shape, that the quantum fields threading through a wormhole would grow unstable as the loop approached closure, building noise, accumulating fluctuations until the throat itself became untenable. The wormhole would not survive long enough to be used as a time machine. It would dissolve, quietly, before the paradox could be written. This is not a proven result. It is a conjecture, supported by partial calculations and physical intuition. But it has a certain coherence to it. The universe, in this view, does not forbid closed time-like curves by decree. It simply makes them structurally fragile. The quantum fields do the work that no explicit law needs to do. Others take a different approach entirely. The Novikov self-consistency principle proposes that the universe does not need to destroy paradoxical wormholes, because paradoxical histories are simply not permitted. Only self-consistent histories can occur. If a traveler went back through a wormhole, they could only do things that had already happened. They could not prevent their own departure, because their departure is part of the history that brought them there. The loop is closed, but it is closed without contradiction. In this view, the past is not a place that can be rewritten. It is a place that has already been written, and the traveler is already in it. There is something almost restful about this idea. The universe as a structure that permits only coherent stories. No loose ends, no erased causes, no events that unhappen. Just a single, self-consistent history, folded back on itself without tearing. Whether the universe actually works this way is not known. Both the quantum instability argument and the Novikov principle are frameworks for thinking, not confirmed descriptions of nature. They sit alongside each other in the literature, patient and unresolved. And beneath both of them lies a deeper question, one that does not depend on travelers or paradoxes at all. The question of what spacetime actually looks like at the largest scales, in its full global shape. Einstein's field equations are local. They describe how matter and energy curve the spacetime immediately around them. They say nothing, directly, about the overall topology of the universe, its global connectivity, the number of handles it might have, whether distant regions are joined by tunnels that the local equations cannot see. Topology is the study of shape in its most fundamental sense, not the precise distances and angles, but the deeper structure, whether a surface has holes, whether it is simply connected or riddled with passages. Two spaces can satisfy identical local equations and still be globally different. One might be simply connected, like a smooth sphere. Another might have handles, like a surface with tunnels running through it. Einstein's equations do not choose between these possibilities. They describe the curvature at each point, but the global arrangement of those points, the way the manifold is stitched together across vast distances, is not fixed by the local physics alone. This means that spacetime could, in principle, include handles, tunnels, connections between regions that are far apart in the ordinary sense, but joined at a deeper level of the geometry, and none of this would violate any local physical law. The equations at every point could be perfectly satisfied. The energy conditions could be met locally, and still the global structure could be something far more intricate than a simple, open expanse. We do not know the topology of the universe. Observations constrain it, but they cannot rule out complexity at scales beyond what we can see. The universe may be simply connected, or it may not be, and the mathematics offers no prohibition either way. This is one of the quieter mysteries in cosmology, not often discussed, because it is so difficult to test, but present, always, in the background of any serious conversation about the shape of space. And then there is the question of what space looks like, not at the largest scales, but at the smallest. John Wheeler, one of the physicists who spent a lifetime thinking carefully about the nature of space-time, introduced a concept he called quantum foam. The idea is this: at the scale of the very small, not the scale of atoms, not even the scale of protons, but far smaller, at the Planck length, space-time may not be smooth at all. The Planck length is roughly 10 to the power of negative 35 meters. It is so small that no instrument we have built, or could conceivably build, can probe it directly. At that scale, the ordinary picture of space-time as a calm, continuous fabric is expected to break down. Quantum effects and gravitational effects become equally important, and the two theories we use to describe them, quantum mechanics and general relativity, do not yet speak the same language. Wheeler's conjecture was that at this scale, space-time seethes, that it is not a smooth surface, but a turbulent froth, constantly fluctuating, constantly producing and destroying tiny structures. And among those structures, he suggested, would be microscopic wormholes, tiny tunnels, forming and collapsing in intervals too brief to measure, connecting points in space-time that are separated by distances too small to imagine. Quantum foam is not an established fact. It is a theoretical picture, an extrapolation from the principles of quantum mechanics applied to the geometry of space itself. We have no direct evidence for it. We may never have direct evidence for it, given how far below any accessible scale the Planck length lies. But the picture has a certain internal logic. If quantum mechanics applies to everything, and as far as we can tell, it does, then it applies to space-time itself. And quantum systems do not sit still. They fluctuate. They explore their possibilities. A quantum space-time would not be a fixed background, but a dynamic, uncertain structure full of transient geometries. The wormholes of quantum foam, if they exist, would be nothing like the traversable tunnels of science fiction. They would be far too small to admit any particle, far too short-lived to carry any signal. They would be geometrical events, not passages, structures that arise and vanish before anything could notice them. And yet, they would be real. Geometry, at its most fundamental level, restless and full of brief connections. Space-time, not as a stage on which things happen, but as something that itself participates, something that fluctuates and reaches and briefly touches itself in places too small to see. The smooth space you move through every day, the quiet dark of this room, the stillness between one breath and the next, may rest at its deepest foundation on something that is not still at all. Something frothing, gently, at a scale so far below perception that it will never disturb a single moment of your sleep. That scale, the Planck length, is worth sitting with for a moment. It is roughly 10 to the power of negative 35 meters, a number so small it resists any honest comparison. If an atom were magnified to the size of the observable universe, the Planck length within that atom would still be smaller than an atom. There is no ladder of analogy that reaches it, only the mathematics, pointing quietly downward into a domain nothing has ever directly observed. This is the scale at which physicists expect quantum gravity to take over, where the smooth, continuous space-time described by general relativity is thought to give way to something else entirely, something whose nature we do not yet know how to write down in full. General relativity is a theory of the large. It describes how mass curves space, how time bends near a heavy object, how the universe expands. It works with extraordinary precision at every scale we can measure, but it assumes space-time is smooth, differentiable at every point, a surface without grain or texture. Quantum mechanics makes no such assumption. It is a theory of discreteness, of probability, of irreducible uncertainty. And when you try to apply its logic to space-time itself, to ask what space-time looks like when you zoom in past every scale we have ever probed, the two theories do not agree. They produce infinities where there should be answers. They describe a domain neither was built to handle. What lies at the Planck scale is, in the most honest sense, unknown. The quantum foam picture, space-time as a froth of microscopic wormholes and transient geometries, is one attempt to imagine it. It is not a confirmed theory, it is a conjecture, a way of taking seriously what the equations seem to suggest when pushed to their limits. And what they suggest is that the smooth space of our experience is, at its foundation, not smooth at all. But even within that picture, the wormholes of quantum foam offer no passage. They are too small by an almost incomprehensible margin, too brief, too unstable. A particle attempting to enter one would find no entrance. A signal attempting to cross one would find no crossing. They are not tunnels. They are geometrical whispers, arising and dissolving in a register of reality that nothing macroscopic will ever touch. And yet, in 2013, two physicists, Juan Maldacena and Leonard Susskind, proposed something that quietly changed the conversation. They noticed something. A coincidence. Perhaps, or perhaps not a coincidence at all. In 1935, Einstein and his colleague Boris Podolsky and Nathan Rosen published two separate papers. One described the Einstein-Rosen bridge, the wormhole solution that emerges from general relativity. The other, written with Podolsky, described what Einstein called a puzzling feature of quantum mechanics, a feature he found deeply uncomfortable. That feature was entanglement. When two quantum particles interact in certain ways, they become correlated in a manner that persists regardless of the distance between them. Measure one particle, and you instantly know something about the other, no matter how far away it has traveled. Einstein, Podolsky, and Rosen argued that this was evidence of something missing from quantum theory, that there must be some hidden information, some local reality that quantum mechanics was failing to capture. They were wrong about that conclusion, as later experiments would show. But the phenomenon they described was real. Entanglement is real. Two particles, separated by any distance, sharing a connection that has no classical explanation. For decades, the Einstein-Rosen bridge and the Einstein-Podolsky-Rosen entanglement were treated as entirely separate ideas. One belonged to general relativity, the other to quantum mechanics. Two different frameworks, two different languages, two different pictures of reality. Maldacena and Susskind looked at them together, and they proposed that ER equals EPR, that the Einstein-Rosen bridge and the Einstein-Podolsky-Rosen correlation are not two different things, but two descriptions of the same thing. That entangled particles are connected by a wormhole, not a large wormhole, not a traversable one, not anything that could carry matter or information from one particle to the other, but a minimal geometric connection, a thread of space-time linking two particles that quantum mechanics says are correlated. The conjecture is written simply, ER equals EPR. 4 letters and a symbol, but what it implies is vast and quiet and still being understood. If it is correct, then entanglement is not merely a statistical correlation, it is a geometric fact. Two entangled particles are, in some precise sense, connected through the fabric of space-time itself. The non-local strangeness that troubled Einstein in 1935 would turn out to be a wormhole, the very structure he had also described in 1935 in a different paper, without knowing the two were related. The same year, the same authors. Two ideas that may be one. There is something almost restful in that symmetry. The way a long question and its answer can sit in the same mind for decades without recognizing each other. The way understanding sometimes arrives not as a new discovery, but as a quiet realization that two things already known were always the same thing. These microscopic wormholes, if ER equals EPR is correct, would be everywhere. Every pair of entangled particles in the universe, connected by a geometric bridge too small and too non-traversable to carry anything, but real, woven into the structure of what exists. The universe, on this picture is not a collection of separate things connected by forces. It is a web of geometric relationships. Entanglement is not something that happens between particles. It is something that space-time does. A reaching, a touching, a connection expressed not in the language of fields and forces, but in the language of geometry. This is still a conjecture. It has not been proven. It has not been derived from a complete theory of quantum gravity, because no such theory yet exists. But it has been taken seriously by many of the physicists working at the intersection of these ideas, because it fits. It resolves certain puzzles. It suggests a picture of reality in which the two great frameworks of modern physics, general relativity and quantum mechanics, are not merely compatible, but deeply unified, at a level we are only beginning to see. And it traces back, quietly, to 1935. To a year when Einstein was troubled by quantum mechanics and trying to understand particles as geometry. When he and Rosen found a bridge in the equations they did not know what to do with. When he and Podolsky and Rosen found a correlation in quantum theory they thought must be incomplete. 2 papers, 2 puzzles, 1 year, and perhaps nearly a century later, one answer beginning to take shape. The wormhole that Einstein found in his equations may not be only a feature of black holes and exotic matter in the large-scale structure of spacetime. It may also be the hidden geometry of the smallest correlations in nature, the thread that runs through every entangled pair, the connection that quantum mechanics describes in probabilities and general relativity describes in curves. The same bridge, seen from 2 different directions. Rest with that for a moment. There is no need to hold it tightly. Let it settle the way a fact settles when it is true and patient, and in no hurry to be understood all at once. The universe has been quietly connecting things across distances since long before anyone thought to ask how. And so we rest here for a moment with that image. The same bridge, seen from 2 directions. It is worth staying with what that means, quietly, before moving on. Geometry and entanglement, the shape of space-time and the correlations of quantum mechanics. These have always seemed like separate languages, describing separate worlds. One speaks in curves and distances and the bending of light. The other speaks in probabilities and superpositions and connections that have no obvious location in space. And yet the ER equals EPR conjecture suggests they are not separate at all. It suggests that the entanglement structure of quantum mechanics and the geometry of space-time are, at some deep level, the same thing, described differently, measured differently, but rooted in the same underlying reality. That is not a small idea. It means that when 2 particles become entangled, when their quantum states become correlated in that quiet, non-local way, something geometric happens between them. A bridge forms, not a tunnel you could travel through, not a passage wide enough for any particle, any signal, any piece of information, but a geometric connection, nonetheless, a thread in the fabric. If the conjecture is correct, these bridges are everywhere. Every entangled pair in the universe, and there are, as far as we can tell, an almost incomprehensible number of them, carries between it a microscopic wormhole, too small to see, too small to use, too small to detect with any instrument we have or could imagine building, but real in the same sense that a curve in space-time is real. The universe, on this view, is not a collection of separate things connected by forces. It is a web of geometry, stitched together at the smallest scales by entanglement. Rest with that for a moment. You do not need to understand it fully. No one does, yet it is a conjecture, not a confirmed theory, a direction the mathematics seems to point, not a destination anyone has reached. But it is the kind of idea that, once encountered, quietly changes the shape of everything around it. And it has already changed something very specific. It has changed how physicists think about one of the deepest puzzles in modern physics. A puzzle that has been sitting, unresolved, for roughly half a century. The black hole information paradox. To understand it, it helps to hold two things gently in mind at once. The first is what a black hole does to information. When something falls into a black hole, a particle, a book, a star, it crosses the event horizon and, as far as the outside universe is concerned, it vanishes. The event horizon is a boundary, a point of no return. Beyond it, not even light escapes. And so whatever fell in seems, from the outside, to be simply gone. The second thing to hold in mind is a principle that sits at the heart of quantum mechanics. The principle that information is never truly destroyed. In quantum theory, the state of a system evolves in a way that is, in principle, reversible. If you knew the complete quantum state of everything now, you could, in principle, reconstruct everything that came before. Information is conserved. It changes form. It disperses. It becomes extraordinarily difficult to recover, but it does not cease to exist. These two things are in tension. If a black hole swallows information and then simply holds it forever, that is already uncomfortable. But in 1974, Stephen Hawking made the tension much sharper. He showed, through a careful calculation combining quantum mechanics and general relativity, that black holes are not entirely black. They glow, very faintly, very slowly, but they emit radiation, a soft, thermal warmth leaking from just outside the event horizon, produced by the behavior of quantum fields in the curved spacetime near the black hole. This is Hawking radiation, and it carries a consequence that Hawking himself found deeply troubling. If a black hole emits radiation, it loses energy, slowly, over an almost unimaginably long time, but steadily. And if it loses enough energy, it shrinks, and eventually, it evaporates entirely. It disappears. And when it disappears, what happens to everything that fell in? If the Hawking radiation is purely thermal, if it is just random warmth, carrying no specific information about what the black hole once contained, then when the black hole is gone, the information is gone with it, not hidden somewhere, not encoded in some subtle form, simply absent from the universe. That would mean quantum mechanics is wrong, or at least incomplete. It would mean information can be destroyed. Most physicists find that very difficult to accept. And so, the paradox sits. A black hole forms. Things fall in. The black hole slowly radiates. And at the end, either the information survives somehow, encoded in the radiation in some form too subtle for Hawking's original calculation to capture, or it is lost, and something fundamental about quantum mechanics breaks down. For decades, this paradox resisted resolution. And then the ER equals EPR conjecture arrived and offered a new way of seeing it. If entanglement is geometry, if every entangled pair is connected by a microscopic bridge, then the Hawking radiation emitted by a black hole is not simply floating free in space, unconnected to what it left behind. It is entangled with the black hole interior. And that entanglement, on the ER equals EPR view, is a geometric connection, a wormhole-like thread running between the radiation outside and the interior within. The information does not escape in any ordinary sense. It does not stream out through the event horizon, but it is not severed from the black hole either. It remains connected. through the quiet geometry of entanglement to what it came from. This does not fully solve the paradox. Physicists are careful about that. The details are still being worked out, and there are aspects of the argument that remain contested and incomplete. But it reframes the question in a way that feels, to many, like genuine progress. It suggests that the interior of a black hole and the radiation it emits are not separate things. They are part of the same geometric structure, the same web of entanglement that, according to the conjecture, stitches the rest of the universe together. The black hole is not a place where the rules break down. It may be a place where the rules reveal themselves most clearly, where the connection between geometry and quantum mechanics, between the shape of space and the correlations of particles, becomes impossible to ignore. And all of this traces back, in some sense, to Hawking's quiet discovery in 1974, a calculation done on paper in the language of quantum field theory and curved spacetime that showed a black hole slowly breathing out warmth into the cold of space. He did not know, when he did that calculation, that it would eventually become a thread in a much larger tapestry, that the radiation he predicted would become central to questions about information and entanglement and the geometry of space-time at its deepest level. That is often how it goes in physics. A result arrives, and it seems to answer one question. And then, slowly, it opens into something much larger than anyone expected. The warmth of a black hole, drifting outward, carrying, perhaps, the faintest geometric echo of everything that ever fell in. Let that settle now. There is no need to hold the details, only the shape of the thing, the sense that the universe keeps its accounts, that what falls in does not simply vanish, that connection, in one form or another, persists. Even here, even at the edge of a black hole, even at the boundary where space and time themselves begin to lose their ordinary meaning, something remains. Something remains, and that word, remains, carries more weight here than it might seem. Because the question that follows from Hawking's calculation is not a small one. If a black hole slowly evaporates, if it radiates away its mass, particle by particle, over timescales so vast they dwarf the current age of the universe, then what becomes of everything that fell in? A star, a cloud of gas, a book, if you like, anything with structure, with information encoded in the arrangement of its parts. Does that information survive? Quantum mechanics says it must. One of the deepest principles in quantum theory is that information is never truly destroyed, that the state of a system, however scrambled, however transformed, can in principle always be recovered. The equations do not permit erasure. And yet, if Hawking radiation is purely thermal, if it is simply warmth, random and structureless, like the glow of an ember that has forgotten what it once was, then the information is gone, truly gone, not hidden, not encoded, not waiting to be recovered, simply absent from the universe. That conflict sits at the heart of what physicists call the black hole information paradox. Two frameworks, each deeply trusted, each tested in its own domain, arriving at answers that cannot both be right. General relativity says the black hole evaporates. Quantum mechanics says the information must persist. And for decades, no one could see how to reconcile them. This is where the ER equals EPR conjecture enters, quietly, with the weight of something that might matter enormously. The suggestion, put forward by Juan Maldacena and Leonard Susskind in 2013, is that the Hawking radiation is not simply drifting away, unconnected to what it left behind. It is entangled with the interior of the black hole. And that entanglement, that deep quantum correlation is not merely a bookkeeping relation. It is, in this framework, a geometric one. The radiation and the interior are connected by something that has the structure of a wormhole. Not a large wormhole, not one you could pass through, but a real geometric bridge woven from the fabric of entanglement itself. The information does not escape by being carried out. It persists because the connection was never fully severed. Let that rest for a moment. The universe keeps its accounts, not by sending information back out through ordinary space, but by maintaining, at some deep level, a geometry of connection that ordinary space does not reveal. Whether this picture is correct, physicists are still working to understand, but it has changed the conversation. It has made the wormhole not just a curiosity of general relativity, but a possible thread in the fabric of quantum mechanics itself. And so we return, gently, to the wormhole as a physical object, or as close to a physical object as the mathematics allows. The most carefully constructed model of a traversable wormhole is called the Morris-Thorne Wormhole, named for Kip Thorne and his student Michael Morris, who worked out its geometry in 1988. It is not a wild or speculative construction. It is a precise solution, a specific way of writing down the curvature of space-time such that a tunnel remains open, with a throat of fixed radius, connecting two regions that might be very far apart. The metric, the mathematical object that describes distances and times in curved space-time, is chosen so that the throat neither pinches off nor expands without bound. It simply holds, still and open, like a passage waiting. But holding it open is not free. The Morris-Thorne metric requires, at the throat, a precise distribution of matter with negative energy density. The exotic matter must be arranged just so, in exactly the right configuration, to counteract the natural tendency of gravity to close the tunnel. Gravity, left to itself, is a closing force. It draws things together. It collapses. A wormhole throat, without something to hold it, would pinch shut in an instant, far faster than any signal could pass through. The exotic matter pushes back. It holds the walls apart. It maintains the geometry against the relentless inward pull. And the requirement is not approximate, it is exact. Even a small perturbation, a slight unevenness in the distribution of exotic matter, a tiny fluctuation in the energy at the throat would be enough to destabilize the whole structure. The throat would either collapse inward, sealing itself off entirely, or expand outward in a way that could not be controlled. There is no gentle middle ground, no room for imprecision. This is part of what makes the Morris-Thorne Wormhole so difficult to take seriously as a physical object, even in principle, not just because exotic matter is hard to come by, but because the stability it requires is the kind of stability that nature rarely offers. Real systems are perturbed. They are nudged by quantum fluctuations, by passing radiation, by the ordinary noise of a universe that is never perfectly still. A structure that cannot tolerate any perturbation is a structure that the universe would dismantle almost immediately. And yet, the model remains because it is exact, and because it asks a precise question: what would it take? What are the minimum conditions? And in asking that question precisely, it has opened doors that vaguer thinking could not. Some physicists have begun to ask whether the requirement for classical exotic matter might be relaxed, whether quantum fields, rather than some exotic classical substance, might be able to provide the negative energy needed to hold a wormhole open. Quantum fields are not quiet. They fluctuate. They carry energy that can, in certain configurations, dip below the vacuum level. The Casimir effect is the most familiar example of this. negative energy appearing between closely spaced plates, not because anything unusual was placed there, but because the geometry of the space itself constrains which fluctuations are permitted. The question is whether similar effects, arising from the geometry of a wormhole throat itself, could generate enough negative energy to sustain the structure. Some theoretical models suggest this might be possible, at least in principle, that a wormhole could, in a sense, help hold itself open, the curvature of its own throat shaping the quantum fields within it in a way that provides the stability it needs. These models are not established physics. They are explorations. Careful, mathematically serious explorations, but explorations nonetheless. The calculations are difficult, and the results depend on assumptions about quantum gravity that no one has yet been able to fully verify. But they point towards something worth holding gently. The possibility that the barrier is not absolute, that the universe's own quantum nature might, under the right conditions, provide what classical matter cannot, that the wormhole might not need to be fed from outside, but might, in some configurations, carry within its own geometry the seeds of its persistence. This is speculative, and it is honest to say so. But it is the kind of speculation that has, more than once in the history of physics, turned out to be pointing at something real. The equations keep producing these structures. The geometry keeps suggesting these connections. And the quantum theory keeps hinting that the connections are not merely mathematical. Something in the deep structure of space-time seems to want to be connected. Whether that wanting is ever realized in a form we could observe, or traverse, or even detect from a distance, that remains open. Quietly open. Like a throat in the fabric of space, holding its shape against the dark. There is a tool physicists use to look at space-time the way you might look at a map of the entire ocean on a single page. It is called a Penrose diagram. And what it does, quietly and precisely, is take the infinite, all of space, all of time, stretching without end in every direction, and fold it into a finite shape that fits on paper. The trick is a mathematical compression, a transformation that preserves the causal structure of space-time, which events can influence which other events, while squeezing infinite distances into finite ones. Light always travels at 45 degrees on such a diagram, and everything else, every slower path through space and time, falls within those lines. What you lose is scale. What you gain is the whole picture at once. And when you draw a Penrose diagram for a black hole, not just the region outside, but the complete, maximally extended solution, something unexpected appears. The geometry does not describe one universe. It describes two. On the left side of the diagram, a region of space-time that looks exactly like the universe we inhabit, flat at large distances, curved near the center, bounded by an event horizon. And on the right side, separated by that horizon, another region, identical in structure, a second exterior universe, as complete and self-contained as our own. Between them, connecting the two, a diagonal bridge. The Einstein-Rosen bridge, visible now, not as an equation, but as a shape. A throat that reaches from one universe to the other, drawn in the geometry of the diagram, like a narrow passage between two vast rooms. And yet, the diagram also shows something else, something the equations had always contained, but that the picture makes undeniable. The bridge does not last. In the maximally extended Schwarzschild solution, the connection between the two exterior universes exists only for an instant. A single moment in the life of the geometry when the throat is open, and then it closes. The singularity sweeps through, and the passage is gone. No signal sent from one exterior universe can reach the other. No light, no particle, no information of any kind. An observer sitting in one of those universes, looking toward the bridge, would find the horizon impassable. They could cross it, yes, but crossing it means falling toward the singularity, not passing through to the other side. The bridge connects two universes that can never communicate. It is a geometric fact with no physical consequence, a tunnel with walls on both ends. This is the Schwarzschild wormhole in its honest form. Not a passage, but a shape. Not a door, but the outline of one drawn in space-time and then immediately erased. For a long time, this seemed to close the question. If the simplest wormhole solution collapses before anything can traverse it, and if keeping it open requires matter that does not exist, then perhaps wormholes are simply a feature of the mathematics, beautiful, precise, and inert. But the universe is not always simple, and not all black holes are the same. The Schwarzschild solution describes a black hole that is perfectly still, no rotation, no charge. A mathematical idealization that captures the essential geometry of gravity but leaves out something that almost every real object in the universe possesses: angular momentum. Stars rotate. The gas clouds that collapse to form black holes rotate. And when a rotating object collapses under its own gravity, the black hole it becomes carries that rotation with it, encoded in the curvature of space-time around it, bending the fabric of space in a slow spiral, like water circling a drain. These rotating black holes are described by a different solution to Einstein's equations, one found not by Schwarzschild, but by Roy Kerr, a New Zealand mathematician, in 1963, and the geometry he found is stranger and in some ways richer than the one that came before. In a Schwarzschild black hole, the singularity is a point, or more precisely, a moment, a place in time rather than space, unavoidable for anything that crosses the horizon, the way tomorrow is unavoidable for anyone alive today. In a Kerr black hole, the singularity is different. It is a ring, a one-dimensional loop of infinite curvature, spinning in the interior of the black hole like a halo of broken geometry. Not a point to be struck, but a circle to be navigated around. And this changes things. In the Schwarzschild geometry, there is no path through the singularity. It is the end, in every direction. But in the Kerr geometry, the ring's singularity has an interior, a region of space enclosed by the ring but not coinciding with it, and a path that passes through the center of the ring, through the hole in the halo, does not pass through the singularity itself. It avoids it. Mathematically, such a path continues. The equations do not terminate. They keep going into a region of space-time that lies, in some sense, beyond the singularity. A region that the Kerr metric describes as having properties quite unlike the space outside. Some solutions to the Kerr metric suggest that this path, through the ring, beyond the singularity, leads not back into the same universe, but into a different region of space-time entirely, a new exterior, as the Schwarzschild solution had two exteriors, but reached now not through a bridge that collapses in an instant, but through a passage that the rotation of the black hole may, in some configurations, hold open longer. This is where the mathematics becomes careful, and honesty requires a pause. The stability of this path is deeply uncertain. The Cauchy horizon, a boundary that appears in the interior of rotating and charged black holes, beyond which the future becomes in some sense unpredictable, is thought to be unstable in practice. Small perturbations near it, the kind that any real and falling matter would introduce, are expected to grow, to amplify, to potentially destroy the smooth geometry that the idealized solution describes. The Kerr solution, in its pure mathematical form, contains a passage through the ring. But the Kerr solution is an idealization, a perfectly rotating black hole in an otherwise empty universe, undisturbed by any infalling matter, any radiation, any quantum effect. Real black holes are not like that. And so the passage through the ring, while it exists in the equations, may not survive contact with reality. The geometry may be too fragile, the perturbations too persistent, the Cauchy horizon too unstable to allow safe passage through. This is not a failure of the mathematics. It is the mathematics being honest about its own limits, showing us a structure that is possible in principle, and then quietly flagging the conditions under which that structure might not hold. The Kerr geometry is, in this way, a kind of invitation and a warning at once. Here is a path. It says, here is a ring you could pass through, a singularity you could avoid, a region of space-time that lies beyond the one you know. And here, also, is the instability that waits at the threshold, the perturbation that grows, the horizon that may not hold. Whether any of this is physically realized, whether rotating black holes in the actual universe contain traversable passages, or whether those passages are always destroyed before they can be used, is a question that sits at the edge of what current physics can answer. The equations point toward the possibility, and then they grow quiet. There is another family of black holes worth resting with for a moment. Not the rotating kind, but the charged kind. Black holes that carry electric charge, described by a solution called the Reasoner-Nordström metric, and which contain, in their interiors, a geometry that once again resembles a tunnel. The mathematics here is different from Kerr's. The singularity is not a ring, but a point. And yet the internal structure of a charged black hole is, in some ways, even more intricate than that of a rotating one. There are two horizons instead of one. An outer horizon, where the escape velocity reaches the speed of light, and an inner horizon, deeper inside, where something stranger begins. That inner boundary has a name: the Cauchy horizon. It marks the edge of predictability itself. Beyond the Cauchy horizon, the equations of general relativity can no longer tell you what will happen next, not because they break down in the way they break down at a singularity, but because the structure of spacetime there allows information from infinitely many different futures to converge on a single point. The future, in that region, is not determined by the past. It branches, or floods, or simply refuses to be pinned down. This is not a poetic description. It is a precise mathematical statement about the causal structure of the space-time. And within that structure, there is again something that resembles a wormhole, a passage, a throat, a geometry that connects regions that would otherwise be entirely separate. But the Cauchy horizon, like the ring singularity of the Kerr solution, carries its own warning. Small perturbations near it, tiny ripples in the gravitational field, the faint radiation that any realistic black hole would accumulate over time, are thought to grow without bound as they approach that inner boundary. A perturbation that is negligible far away becomes enormous near the Cauchy horizon. The geometry amplifies it, focuses it, until what began as a whisper arrives as something the structure may not survive. This is sometimes called the blue shift instability. The infalling radiation is compressed and blue shifted to arbitrarily high energies as it approaches the inner horizon, and those energies, in a realistic black hole, would likely destroy the wormhole-like passage before anything could use it. The Reasoner-Nordström geometry, like the Kerr geometry, offers a tunnel in its equations, and then, quietly, undermines it. Both solutions point toward the same pattern. The mathematics permits these internal structures, these passages, these connections, these regions that lie beyond the familiar. And then the mathematics also shows you the instability that waits at the threshold, the perturbation that grows, the horizon that may not hold. Whether this means the passages are truly destroyed in every realistic case, or whether some more complete theory of quantum gravity would stabilize them in ways we cannot yet see, that remains an open question. One, the equations raise and then leave unanswered. There is a different way to look for wormholes. Not by falling into a black hole and hoping the geometry holds, but by watching the sky. Light does not travel in straight lines through a curved universe. When it passes near a massive object, a star, a galaxy, a black hole, the curvature of spacetime bends its path. The light arrives at your eye from a slightly different direction than the source actually occupies. This is gravitational lensing. It was predicted by general relativity and confirmed during the solar eclipse of 1919, when stars near the edge of the sun appeared shifted from their expected positions. The sun's gravity had bent the light on its way to Earth. Since then, gravitational lensing has become one of the most productive tools in observational astronomy, used to map dark matter, to find distant galaxies, to detect planets around other stars. And it could, in principle, reveal a wormhole. A wormhole mouth sitting in space would bend light just as a massive object does, but the signature it would leave on the sky is different from the signature of a black hole. A black hole, viewed directly, casts a shadow. Its gravity is so strong that light falling too close cannot escape. What remains is a dark region surrounded by a bright ring, the photon sphere, where light orbits just at the edge of escape. A wormhole mouth would produce something subtly different. There would still be a bright ring, light bending around the throat, curving back toward the observer, forming that same luminous circle. But at the center, instead of darkness, there would be light. The light coming through from the other side. Whatever lies at the far end of the wormhole, another region of space, another point in the same galaxy, another universe entirely. Its light would travel through the throat and emerge at the mouth, filling the center of the ring with a faint, diffuse brightening. A black hole shadow is dark at its heart. A wormhole shadow, if that is even the right word, would glow. This distinction is subtle. The difference between a dark center and a faintly bright one, at the distances involved, would require extraordinary precision to detect. But it is, in principle, a real observational difference. Astronomers have thought carefully about what such a signature would look like, how it would vary depending on the size of the throat, the distance to the far mouth, the nature of whatever matter or radiation might be passing through. The model suggests that with sufficiently precise instruments, the two signatures could be told apart. And there are instruments now that approach that precision. The Event Horizon Telescope, the global network of radio observatories that produced the first image of a black hole shadow, the one at the center of the galaxy M87, operates at a resolution that begins to enter the range where some wormhole signatures might, under the right conditions, become distinguishable. Not that any such signature has been found. No wormhole has been detected. No bright center where darkness was expected. No anomalous lensing pattern that resists explanation by ordinary massive objects. But the search is no longer purely theoretical. There are now real observations, real images, real data. And within that data, the question can at least be asked: The universe is large enough and old enough that the absence of a detection so far says relatively little. A wormhole would have to be close enough and large enough and oriented correctly and surrounded by the right kind of radiating matter for its signature to stand out against the noise. Most of the universe remains unexamined at that resolution. Most of the sky has not been looked at with eyes sharp enough to tell the difference. So the question stays open. Not with urgency, not with the restless energy of a search that expects to find something soon, but with the quiet patience of a science that has learned to hold its possibilities lightly, to keep the question alive without demanding an answer before the evidence is ready. Somewhere in the sky, there may be a ring of light with a bright center instead of a dark one. A mouth, a throat, a passage to somewhere else. Or there may not be. The equations do not require it. They only permit it. And the sky, so far, has not said either way. And the telescope that first gave us a black hole shadow, the Event Horizon Telescope, already operates at a resolution where some of those signatures might, in principle, become visible. It is a network of radio dishes spread across the surface of the Earth, from Chile to the South Pole, from Hawaii to Spain. Working together, they form a single instrument roughly the size of the planet. And in 2019, that instrument produced an image, a glowing ring of heated gas surrounding a dark center, the shadow of a black hole at the heart of a galaxy called M87, 55 million light-years away. That image was a confirmation, a quiet, careful confirmation that the mathematics of general relativity, written down more than a century ago, describes something real. And the same instrument, turned toward the right object, might one day see something different. Not a dark center, but a bright one. A ring of light that does not hollow out at its heart, but instead brightens. That is what a wormhole mouth is expected to produce. If it is large enough, and if the conditions around it are right, the lensing geometry is different. The way light bends around a throat rather than a horizon leaves a different mark on the image. Astronomers have worked out, at least in theory, what that mark would look like, how it would differ from a black hole shadow in ways that careful measurement could, in principle, distinguish. The resolution required is at the edge of what current technology can achieve, perhaps beyond it for most candidates, but not infinitely beyond it, not forever out of reach. So the search is not closed. It is simply waiting for the instruments to catch up with the question. And the question itself has more than one form. There is a distinction, quiet but important, between two kinds of wormhole that the mathematics permits. One kind connects two distant points within the same universe, the same spacetime, the same cosmic history, just separated by an enormous stretch of ordinary space. These are called intra-universe wormholes, a shortcut, in a sense, folded into the fabric of a single continuous space. The other kind connects two separate universes entirely, two distinct spacetimes that share no common region, no common past, no common sky. These are called inter-universe wormholes, and they raise a different order of question, not just how far, but where, not just across space, but across the boundary of existence itself. The mathematics does not forbid either kind. The field equations are indifferent to which version they describe. They produce both, given the right conditions, with the same quiet neutrality they bring to everything. Whether the second kind, the inter-universe kind, has anything to connect to depends on a question that sits at the edge of what physics can currently say. There is a framework built from the theory of cosmic inflation that suggests our universe may not be alone. Eternal inflation, as it is called, describes a process in which the rapid expansion of space in the early universe never fully stops. In most regions, inflation ends, and a universe like ours condenses out of the cooling energy. But in other regions, inflation continues. And from those continuing regions, new pockets of settled spacetime bud off, each with its own physics, its own constants, its own long history. The result, if this picture is correct, is a vast and perhaps infinite collection of causally disconnected regions, universes that can never communicate with one another through ordinary spacetime, because the space between them is expanding faster than any signal could cross it. These regions are, by definition, beyond our observational horizon. We cannot see them. We cannot reach them. We cannot confirm they exist. And yet the mathematics of eternal inflation predicts them, and the mathematics of wormholes permits connections between them. Two frameworks, each uncertain on its own, pointing toward the same strange possibility that the universe we inhabit may be threaded somewhere to places we will never otherwise know. This is the kind of thought that arrives quietly, in the dark, and asks nothing of you. It does not require a response. It only asks to be held for a moment, gently, before it dissolves back into the larger silence. No observational evidence for a wormhole has been found. Not one. Not a lensing signature that could not be explained another way. Not a gravitational signal that demanded a throat rather than a merger. Not a pattern in the cosmic microwave background that pointed to a connection between regions that should be separate. The sky, examined as carefully as we have examined it, has not yet offered that. But the universe is very large, and the absence of a detection is not, by itself, evidence that there is nothing to detect. It is evidence only that we have not found it yet. In the places we have looked, with the tools we have used, most of the universe is beyond our reach. Most of it is beyond our sight. The observable universe, the sphere of space from which light has had time to reach us, is vast beyond ordinary comprehension. And even within that sphere, the fraction we have examined at the resolution required to distinguish a wormhole from a black hole is extraordinarily small. The silence of the sky on this question is not a verdict. It is simply the current state of a search that has barely begun. And so the question rests, not answered, not abandoned, just resting, the way a long calculation rests on a page when the mathematician has stepped away for the night. There is one more thread to follow before the mathematics of wormholes settles into stillness. Light moves through space at a fixed and finite speed, roughly 300,000 kilometers every second. In a single year, it travels a distance so large that the number of kilometers required to express it has 13 digits. And yet, on the scale of the universe, even that speed is slow. The nearest star beyond our sun is more than 4 light years away. The center of our galaxy is 26,000 light years away. The galaxy M87, whose black hole we have imaged, is 55 million light years away. To travel between these places through ordinary spacetime, following the ordinary paths that space provides, would take an ordinary traveler an ordinary and impossible amount of time. The speed of light is not just a speed. It is a boundary, a fundamental limit woven into the structure of space-time itself. Nothing carrying information, nothing with mass, nothing that could be called a signal can move through ordinary space faster than light moves. This is not a technological limitation. It is not a barrier that a more advanced civilization might one day engineer around. It is a feature of the geometry of space-time, the same geometry that produces wormholes as solutions. And this is where the two ideas meet, quietly, in the dark. A traversable wormhole would not allow anything to move faster than light locally, at every point along the path, through the throat, through the exotic matter, through the curved geometry of the passage. The traveler would be moving at ordinary speeds, and yet the effective distance between the two mouths could be far shorter than the distance through ordinary space. Not faster than light, but shorter than the path light would otherwise have to take. The universe's speed limit would remain unbroken, and yet the journey would be, in some meaningful sense, shorter than the universe intended. Whether that is possible, whether the geometry permits it, whether the matter required to sustain it can exist, whether the universe allows it without unraveling something else, remains, as it has always remained, an open question, held lightly in the dark, where all the deepest questions eventually come to rest. There is another proposal that lives in the same quiet neighborhood of theoretical physics. A different idea, arrived at by a different path, that reaches the same strange conclusion. In 1994, a physicist named Miguel Alcubierre found a solution to Einstein's equations that described a region of space contracting ahead of a traveler and expanding behind. A bubble of distorted geometry, carrying its contents forward, not by moving through space, but by moving space itself. The traveler inside the bubble would feel nothing unusual, no acceleration, no force, no sense of speed. They would simply sit, and the geometry around them would shift, and they would arrive. The principle is the same one that governs wormholes. At every point, locally, nothing exceeds the speed of light. The traveler is at rest within the bubble. It is the fabric itself that moves, and the fabric, as far as we know, is not bound by the same limit. And yet, the Alcubierre drive requires exotic matter. The same exotic matter that a traversable wormhole requires, matter with negative energy density, matter that would need to exist in quantities and configurations that no known physics can produce. The two ideas, the wormhole and the warp drive, are not the same. They are different geometries, different solutions, different shapes of curved space-time, but they share a foundation, and that foundation is the same wall: negative energy. The thing the universe seems to permit only in whispers, in the narrow gap between two conducting plates, in the faint quantum corrections to otherwise ordinary fields, but never in the abundance these solutions demand. It is as if the equations are generous with their promises and careful with their permissions. They will show you the door. They will describe its dimensions in precise mathematical detail. They will tell you exactly what kind of key is required. And then they will tell you, quietly, that the key may not exist. Both proposals remain exactly where they have always been: beautiful, consistent, and suspended, for now, just beyond the reach of anything we can build or find or hold. There are other corners of theoretical physics where wormholes appear, not as engineering proposals, but as mathematical structures embedded in deeper frameworks. String theory, the attempt to describe all fundamental particles and forces as the vibrations of tiny one-dimensional objects, predicts the existence of extra spatial dimensions. Not the three dimensions of ordinary space, not the one dimension of time, but additional dimensions, curled or compactified, too small to detect directly, woven into the fabric of reality at scales far below anything we can probe. In some of these models, the universe we inhabit is a surface, a brain, floating within a higher dimensional space. And in that higher dimensional space, other brains may exist, other surfaces, other regions, separated not by distance within our three dimensions, but by distance through the extra ones. A wormhole, in this picture, would not need to tunnel through our familiar space at all. It could pass through the higher dimensional bulk. A shortcut not just across the universe, but through dimensions we cannot see or touch or measure. This is speculative. String theory itself, for all its mathematical richness, has not yet made predictions that experiments have confirmed or denied. The extra dimensions remain theoretical, the brains remain theoretical, and the wormholes that might connect them remain theoretical twice over. But the geometry is consistent. The mathematics permits it. And in physics, that is not nothing. There is one more place where wormholes appear, and this one is different in character from all the others. It is not a proposal for travel. It is not a solution waiting for exotic matter. It is a correspondence, a precise mathematical relationship between two very different descriptions of reality. It is called the ASCFT correspondence. The name is dense, but the idea beneath it is worth sitting with for a moment. Anti-de Sitter space is a particular kind of spacetime, one with a specific, uniform negative curvature, like the inside of a saddle extended in all directions. It is not the space-time we live in. Our universe appears to have a small positive curvature, not a negative one. But anti-de Sitter space is mathematically tractable in ways our own space-time is not, and physicists have studied it carefully for decades. The correspondence says this: a theory of gravity, including wormholes, black holes, all the curved geometry of general relativity, living inside an anti-de Sitter space, is mathematically equivalent to a quantum field theory living on the boundary of that space. The boundary has one fewer dimension than the interior. The physics on the boundary contains no gravity at all, and yet the two descriptions are, in a precise and calculable sense, the same. What is a wormhole in the interior corresponds to something specific on the boundary. It corresponds to entanglement. Two regions of the boundary quantum field theory that are entangled with each other, sharing quantum correlations across space, correspond, in the interior description, to those regions being connected by a wormhole. This is the ER equals EPR conjecture made concrete, made calculable, made testable, at least within the mathematical framework. And the A's ACFT correspondence is not speculative in the way that string theory's extra dimensions are speculative. It is one of the most precisely tested ideas in theoretical physics, not tested by experiment in the traditional sense. We cannot build an anti-de Sitter universe in a laboratory, but tested by calculation, by consistency, by the fact that predictions made on one side of the correspondence match predictions made on the other, again and again, across thousands of papers and decades of work. The correspondence holds. And if it holds, then the connection between wormholes and entanglement is not a metaphor. It is not an analogy. It is a mathematical identity. Two entangled particles are, in some precise geometric sense, connected by a bridge. Not a bridge you could travel through. Not a bridge that carries information or matter or any signal at all. But a bridge that is, in the language of the equations, real. The geometry of spacetime and the entanglement structure of quantum mechanics are not two separate things that happen to resemble each other. They may be the same thing, described from different angles, in different languages, arriving, slowly, at the same quiet truth. This is where the physics of wormholes has arrived, for now. Not at a tunnel you could step into, not at a shortcut mapped and measured and ready to use, but at something stranger and, in its own way, more profound. The suggestion that the fabric of space, the geometry that holds everything in place, that curves around mass, that bends the path of light, may be woven, at its deepest level, from the threads of quantum connection. That the reason distant regions of space-time are separate is not merely that they are far apart, but that they are not entangled. And that where entanglement exists, geometry follows. Quietly, without announcement, a bridge forming not from exotic matter or enormous energy, but from the simple fact that two things somewhere in the universe share a quantum state. This is not a settled idea, it is a direction, a shape that the mathematics keeps suggesting, from multiple angles, in multiple frameworks, with a consistency that is difficult to ignore. And so the wormhole, which began as an uninvited solution to a set of equations in 1935, has become something else entirely. Not just a tunnel through space, but a question about what space is made of and what it means for two things to be connected at all. There is another place where wormholes appear, not in the smooth, curved space-time of general relativity, not in the entanglement structure of quantum field theory, but in a framework that begins by questioning something most physicists have always taken for granted: the assumption that space-time is continuous. Loop quantum gravity is one of the most serious attempts to build a quantum theory of gravity from the ground up, and it begins with a different picture of what space actually is. Not a smooth fabric that can be stretched and curved without limit, but something granular, something built from discrete, indivisible units, tiny quanta of geometry, woven together into the texture of space itself. In this picture, there is no such thing as a region of space smaller than the Planck length, roughly 10 to the power of -35 meters, a scale so small it has no analogy in ordinary experience. At that scale, the smooth continuum simply ends, and what lies beneath it is a kind of quantum architecture, a network of nodes and links, each carrying a small, definite amount of geometric information. Space, in loop quantum gravity, is not a stage on which things happen. It is itself a physical thing, quantized, relational, built from pieces. And in that architecture, wormholes appear again. Not as solutions to a classical metric equation, but as features of the quantum geometry itself. Connections between distant nodes in the network that create shortcuts through the fabric. Handles in the topology of the quantum structure, arising not from exotic matter or special initial conditions, but from the way the quantum geometry is assembled. This is a different kind of wormhole. Quieter, in a way, less dramatic than the traversable tunnels of science fiction, less abstract than the entanglement bridges of ER equals EPR, but present, nonetheless, woven into the mathematics of a framework that does not yet have all its pieces in place, but that takes seriously the idea that space is not what it appears to be at the scales we can see. And this is where all the threads converge. Every approach to quantum gravity, string theory, loop quantum gravity, the as-CFT correspondence, the ER equals EPR conjecture, arrives, by its own path, at something wormhole-like. The details differ. The language differs. The mathematical structures are sometimes barely recognizable as describing the same thing. And yet the shape keeps appearing. A connection between distant regions. A bridge through the geometry. A tunnel that the mathematics insists on drawing, even when no one asked for it. Which brings us to the question that sits beneath all of this. Not whether wormholes are useful, not whether they could ever be traversed, but whether they exist at all. And the honest answer, the only answer that the current state of physics permits, is that we do not know. Because the question of whether wormholes can exist is not, at its core, a question about exotic matter or energy conditions or the stability of a particular metric. It is a question about the quantum nature of gravity, about what space-time is, at the deepest level, and what rules govern its behavior when the smooth classical picture breaks down. And that theory, a complete, consistent, experimentally confirmed theory of quantum gravity, is something physicists do not yet possess. General relativity describes gravity with extraordinary precision at the scales we can measure. Quantum mechanics describes the behavior of particles and fields with extraordinary precision at the scales we can probe. But the two theories, taken together, are not fully compatible. They speak different mathematical languages. They rest on different assumptions about the nature of reality, and in the places where both should apply, near singularities. At the Planck scale, in the earliest moments of the universe, they fall silent, or contradict each other, or produce infinities that signal the edge of their own validity. A wormhole, in its most interesting forms, lies precisely in that gap. It requires a regime where quantum effects and gravitational effects are both important, where the smooth spacetime of general relativity is no longer reliable, and where the quantum theory that should replace it is not yet fully written. So we are left, for now, with solutions. Mathematical solutions, each one carefully derived, each one internally consistent within its own framework, each one pointing toward the same general possibility, and each one, when examined closely, carrying a flaw that keeps it just out of reach. The simplest wormhole collapses before anything can cross it. The traversable wormhole requires matter with properties that no known substance possesses. The rotating black hole offers a path through its ring, singularity, but the stability of that path dissolves under scrutiny. The charged black hole contains a Cauchy horizon where predictability ends and perturbations grow without bound. The quantum foam wormholes are real, perhaps, but microscopic beyond any conceivable use. The entanglement bridges are non-traversable by construction. Every door, examined carefully, turns out to be a wall. And yet, the equations keep producing them. Quietly, persistently, across frameworks that were built independently, by different people, with different assumptions, asking different questions. The wormhole keeps appearing in the answer, not because anyone put it there, but because the mathematics of space-time seems to require it, or at least to permit it, in ways that are difficult to dismiss. There is something worth sitting with in that. The universe is under no obligation to make its deepest structures accessible to us. It is not arranged for our convenience. It does not owe us traversable tunnels or shortcuts through space or any of the things we might wish for. It only has to be what it is. And what it is may include structures we cannot reach, cannot build, cannot use, and cannot yet fully describe. Structures that are real in the mathematical sense, consistent solutions to the equations that govern reality, without being real in the sense of something you could ever touch or enter or observe directly. This is not a failure of physics. It is simply the shape of the territory. We are creatures who evolved to navigate a world of moderate speeds and moderate scales. A world where spacetime is flat enough to ignore, where quantum effects are small enough to overlook, where the topology of space is simple enough that it never comes up. We built our intuitions in that world, and now we are trying to use those intuitions to understand a universe that operates, at its extremes, by rules our intuitions were never designed to grasp. The wormhole is one of the places where that gap becomes visible, where the mathematics runs ahead of the physics, and the physics runs ahead of the experiment, and the experiment has not yet arrived. And so we hold it lightly. This idea that space might be connected in ways that distance conceals, that 2 points separated by 1 billion light years might be, in some geometric sense, adjacent, that the fabric of space-time is not simply a backdrop, but a structure with topology, with handles, with bridges, a structure that is still, after nearly 90 years of study, not fully understood. Whether wormholes exist as physical objects somewhere in the universe, threading through the space between galaxies, whether they exist as quantum connections, microscopic and non-traversable, woven into the entanglement structure of everything, or whether they exist only as solutions on paper, beautiful and consistent and forever beyond the reach of any physical process. They have already changed something. They have changed how we think about space, about what it means for two places to be separate, about whether the geometry we see is the geometry that is, about the relationship between gravity and quantum mechanics, between entanglement and distance, between the shape of the universe and the information it contains. The equations that produced them in 1935 were not looking for them. And yet there they were. Quiet, persistent, patient, waiting in the mathematics like something the universe had always known and was only beginning, slowly, to say, "You have not specified which facts to cover in this section." The outline lists 72 facts, but the task says covering these facts, and then nothing follows. Could you let me know which fact numbers you'd like this section to cover? Since no specific fact numbers were provided, I'll cover the final stretch of the outline, facts 59 through 72, which form a natural closing movement. No wormhole has ever been observed. Not one. Every telescope ever built, every detector ever tuned, every image ever captured of the deep sky, none of them has returned with proof that a tunnel through space-time exists. And yet the absence of a thing is not the same as its impossibility. The universe is very large, and we have looked at very little of it. There is a speed that nothing can exceed, the speed at which light moves through empty space, roughly 300,000 kilometers every second. That limit is not a rule imposed from outside. It is woven into the structure of space-time itself. And a wormhole, if one could be held open, would not break that rule. It would simply go around it. An object passing through a wormhole would never move faster than light in its own local neighborhood. It would simply emerge somewhere else, somewhere that would have taken light itself an enormous time to reach by the long way. The shortcut does not violate the law. It quietly sidesteps it. There is another proposal that works the same way, a theoretical construct called the Alcubierre drive, which would compress space-time ahead of a vessel and expand it behind, carrying the vessel forward like a wave carries a boat. The vessel itself would not move through space. Space would move around it. And like the wormhole, it requires exotic matter with negative energy density, the same barrier, the same silence where a solution should be. Both ideas live at the same edge, the place where the mathematics is clear and the physics is not yet ready. Some approaches to unifying gravity with quantum mechanics suggest there may be more dimensions of space than the three we move through. In certain versions of string theory, our universe is a surface, a brain, floating within a higher dimensional space. And in that higher dimensional space, wormhole-like connections between brains might be possible passages that would look, from inside our three dimensions, like nothing at all, until something emerged from one. These are not predictions. They are possibilities. Shapes that the mathematics permits without yet insisting upon. There is a correspondence in theoretical physics between a particular kind of curved spacetime and a particular kind of quantum field theory living on its boundary. In this correspondence, a wormhole threading through the interior of that curved space corresponds to something on the boundary, a pattern of entanglement between quantum fields. The two descriptions are equivalent. The wormhole in the geometry and the entanglement in the quantum theory are, in some precise mathematical sense, the same thing. This is not a loose analogy. It is one of the most carefully tested relationships in all of theoretical physics. And it suggests that the connection between wormholes and entanglement, that quiet conjecture from 2013, is not merely poetic. It may be pointing at something true. Wormholes appear in another framework as well, one that builds space-time not from a smooth fabric, but from discrete quantum pieces, the way a mosaic is built from individual tiles. In loop quantum gravity, space itself is granular at the smallest scales, and wormhole-like structures emerge naturally from the way those grains connect. The geometry is different, the language is different, but the tunnels keep appearing. Across general relativity, across string theory, across loop quantum gravity, frameworks that disagree about almost everything, the wormhole persists. Not as an observation, not yet as a confirmed prediction, but as a shape that the mathematics of spacetime seems to prefer. And this brings us to something quiet and important. The question of whether wormholes exist is not, at its heart, a question about tunnels. It is a question about the nature of gravity itself, about what space and time actually are when you look closely enough, about whether the smooth geometry of Einstein's equations gives way, at the smallest scales, to something stranger and more connected. We do not yet have a complete theory of quantum gravity. We have pieces, beautiful pieces, that fit together in some places and refuse to fit in others. The wormhole sits at the boundary between those pieces, a shape that appears in all of them. That may be the clue that eventually shows how they join. Every wormhole solution found so far carries a flaw. Some collapse before anything can pass through. Some require matter that cannot exist in the quantities needed. Some lead to loops in time that the universe may simply refuse to allow. And yet, the equations keep producing them. Quietly, persistently, as if space-time itself is trying to say something it does not yet have the language to say clearly. There is something worth sitting with in that. The universe is under no obligation to make its deepest structures accessible to us, only to make them real. Whether a wormhole is a physical tunnel you could pass through, or a quantum thread connecting two entangled particles, or only a solution on paper that nature never chose to build, it has already changed something. It changed how we think about the shape of space, about whether two distant points are truly separate, about whether the geometry of the cosmos and the entanglement of its smallest pieces are, at some level, the same story told twice. That is not nothing. That is, perhaps, everything. The night is very quiet now. Somewhere, at a scale far smaller than any atom, space-time may be threaded with passages too tiny to see and too brief to enter. Microscopic bridges flickering in and out of the quantum foam, connecting points that are, in every ordinary sense, unreachable from one another. You will never see them, but they may be there, all around you, beneath you, woven into the floor of reality itself. The same equations that describe the pull of the Earth beneath you, the orbit of the moon above you, the slow drift of galaxies across the dark. Those same equations, followed quietly to their conclusions, produce this: a tunnel, a bridge, a place where here and there become, for a moment, the same. Let that settle. There is no need to hold it. Just let it rest somewhere at the edge of thought, the way a distant light rests on the surface of still water. Present, soft, not asking anything of you. The equations are still running somewhere, in the minds of people who will not sleep for hours yet, tracing the geometry of spaces you will never visit. And you are here, breathing slowly. The weight of the day already distant. Space-time curves around every mass, every warmth, every quiet body at rest. It curves around you now. gently, the way it always has, the way it always will. And somewhere in the deep structure of all of this, perhaps a bridge, perhaps a thread, perhaps just the shape of something we do not yet have words for, waiting patiently in the dark.